Hey folks, welcome back to Anish Learns to Code. Today we will be solving question number 7 on LeetCode algorithms, reverse integer. This video is divided into 3 sections. First is the problem, then the solution or algorithm, and the third, solution in Python. All the links are there in description if you want to jump to any specific time frame, and there's also an analogous video, exactly same but with solution in Java. So if you would like to have a look at that. Let's get started. So here we are with the problem, reverse integer. Given a signed 32-bit integer x, return x with its digits reversed. So if reversing x causes the value to go outside the 32-bit signed range, then return 0. Okay, assume the environment does not allow you to store 64-bit integers, signed or unsigned. This question does make a lot more sense in programming languages that by default support 32-bit signed integers, so like C, C++, Java. We can obviously solve this question in Python as well, but it just makes more sense, I would say, in Java or C++. Let's have a look at the algorithm. Alright, so here goes. We have some number 123 and we have to reverse it. So the answer should be 321. This is how we will approach this problem. We will have our initial number x, which is 123, and we will have a result, which is initially 0. Now we will iterate on our number 123, and in each iteration we will update the value of result so that it becomes 321. This is how we do it. In our first iteration, result will be equal to 0 multiplied by 10 plus 3, and it will become 3. In our second iteration, our result will be equal to 3 multiplied by 10 plus 2, and it will become 32. In the next iteration, our result will become 32 multiplied by 10 plus 1, and it will become 321. Voila. So this is how we will approach it. Let me write this down formally. So this will be our loop. We will have a while loop, and this loop will work for as long as x is greater than 0. So every time the value of result will be 10 times the previous value, whatever the result was, plus the last digit of x. What is the last digit of x? The last digit of x is x modulus 10. So let us say that we have this number 1054. 1054 modulus 10 will give us 4. 105 mod 10 will give us 5. So if we take any number x and take modulus 10 with it, we get the last digit. So we have now updated the value of result. We now need to update the value of x. So let us say that x is currently 1054. 1054, let me just write this down here. 1054 divided by 10 is 105.4. If we take the floor, so floor is a function in mathematics which returns the same integer or the lowest integer or the least smallest integer. So for 105.4, the smallest integer less than 105.4 is 105. This will be equal to, let me just write this down over here, 105. Similarly, 105 divided by 10 is 10.5. Floor of 10.5 is 10. 10 divided by 10 is 1. Floor of 1 is 1. And 1 divided by 10 is 0.1. Floor of 0.1 is 0. So if you observe, there's a pattern. When we have 1054, we divide by 10 and take the floor, we get 105. When we have 105, we divide by 10, take the floor, we get 10. When we have 10, we divide by 10, take the floor, we get 1. And similarly with 1, dividing by 10, take the floor, we get 0. So we can, by performing this operation continuously, we can reduce our number. So if we have 1054, we'll get 105, then 10, then 1, and then finish, nothing. So this is what we write. We say x is equal to x divided by 10 and the floor of that number. By performing this operation, at the end of the day, we can simply return the result, which is r. This is the result. And we can have a further check that if initially the number was negative, then we need to return negative of r. Otherwise, we need to return the result as it is. Okay, so this was the approach. Now let us discuss an additional constraint. The additional constraint that has been imposed on us by LeetCode is that the final result must be within a certain range. So it has to be in the valid 32-bit signed integer range. The solution, how can we accomplish that? So let us say this is how a computer stores numbers. So for us in maths, we can have numbers from negative infinity to positive infinity. We don't have any range or limit on numbers. If you say a number as large as 100000000, like I will not say that this number is too large or this cannot be stored. But for the computer, there are numbers that are too large and cannot be stored. For a 32-bit signed integer, this is the range. The smallest number is minus 2 to the power 31, and the largest number is 2 to the power 31 minus 1. And you have to remain within this range. So let us say that we are given some number x by LeetCode, and we need to reverse this number x. And we initially start with our resultant value. So let us say that we have r, which is initially equal to 0. So let us say after the first iteration we have r1, in the next iteration we have r2, in the next iteration we have r3, in the next iteration we have r4. Finally we get this result with this capital R. There's nothing wrong in this. If your result is in the valid range, that is a valid result. Nothing wrong in that. But it is absolutely possible, as you're iterating, your result crosses the threshold, crosses the bound of 2 to the power 31 minus 1. And because it has crossed the 32-bit signed integer value, how Java and other programming languages treat this bound is, when a number crosses this, it cycles back. So if you're at 2 to the power 31 minus 1, which is like infinity, the largest number, and if you take another step, you'll go all the way to negative infinity. So you'll go all the way to minus 2 to the power 31 if you take one more step after this. And then when you iterate further, you are now over here. So when you cross the bound, you'll end up on the negative side. So now how do we check whether we have crossed the bound or not? So with the initial approach that many people have is, if the number becomes, during your while loop, if ever your number becomes negative, that means you have crossed the bound. This approach will not work. Why will this approach not work? Let us say that you have this some number r, and in the next iteration you have 10r plus a, where a is any constant between 0 to 9. This is like saying r plus 9r plus a. 9r plus a is not guaranteed to be either positive or negative. It is such a large number that it can cross the bound and come back all the way to the positive. It can cross the bound maybe 3-4 times. And after crossing the bound 3-4 times, it is not guaranteed that it will land on the negative side. It is absolutely possible that you were standing over here and then you added such a large number that you spiraled all the way back 2-3 times into positive region. And you're once again now in the positive region. So your check whether the number is negative or not failed. The number did cross the bounds, but it came back to the positive side. It did not enter the negative side. So that is why checking whether a number becomes negative or not is not valid. So how do we check it? We can check it by using this relation. We know that r1 is equal to 10 times r0 plus some constant a1. We know that r2 is equal to 10 times r1 plus some constant a2. And similarly, we know that for any rn, it is equal to 10 times rn minus 1 plus an. We can use this relation. This relation implies that rn minus 1 is equal to rn minus an divided by 10. That means that whatever new value for result that you're getting, in each iteration when you get a new resultant value, that new resultant value has to agree to this equation. If that new resulting value does not agree with this equation, that implies that you have crossed the bounds and you have jumped somewhere, either negative or positive. It will not agree with this. So in each iteration, if you make sure that this condition is true, if you check this condition every time, and as long as this condition holds, you are guaranteed that you are in a valid 32-bit signed integer range. Okay, problem solved. Now we can further reduce this as well. This condition, because when we perform this division by 10 operation in any programming language, C, C++, it will automatically reduce it to a floor integer constant. So this relation can actually also be written that rn minus 1 is actually equivalent modulus 10 to rn. So that's like saying your new value rn divided by 10 floor should be equal to rn minus 1. And this is our final condition that we have to check. I can also prove this. Let us say that you have some number 123. Your resultant value initially is 0. This is like r0, and r1 will be 3, r2 will be 32, and r3 will be 321. So let us start with r1. r1 divided by 10, floor of that, 0.3, floor of 0.3, 0. which is absolutely correct. So see, R1 divided by 10 floor is equal to R0. R2 divided by 10 floor, which is equal to 32, divided by 10 floor is equal to 3, which is equal to R1. Correct. Similarly, we can say 321 divided by 10 and the floor of that is equal to 32, which is equal to R2. That is absolutely correct. So with every iteration, the equation Rn by 10 floor of that should be equal to Rn minus 1 is satisfied. And as we can clearly see, as long as this equation is satisfied, we are in the green and we can return the result. If at any point of time this equation is not satisfied, simply return 0 and call it a day. Now let us discuss the time and space complexity of this problem. The space complexity is very straightforward. We are getting one variable x in a function. We are making our own variable result. We can make another Boolean variable to store whether the number was negative or not. So we are making a fixed amount of variables. The space complexity is constant. Okay, that's done. We can write it over here. Space complexity constant. Now we'll discuss time complexity. The time complexity for this problem is the number of digits that you have in your number. So let us say that you have some number 3, 2, 1, 5, 4. This is a 5-digit number because there are 5 digits. So when you're performing your iterations, when you're iterating over this number, you will work for every digit. So you'll work basically 5 times. So the time complexity for this problem is the number of digits that you have in your number x. The number of digits that you have in your number x is log to the base 10 of x. So the time complexity for this problem is log of x, because this is how many times your loop will run. This is the number of iterations in your program, and for each iteration you're performing constant time operation. You're performing arithmetic operations, multiplication, addition, which take constant time. So the space complexity is constant. The time complexity is log of x. I'll see you in the solution. Here we are. Let's also have a look at, okay, we go to Python 3. I'll take this boilerplate code from here. After taking the boilerplate code, let's write it down. So initially we have a number x, we have our result 0. We'll iterate on a number as long as x is greater than 0. We also need to make a check. Is our number negative? So if x is less than 0, that means it is negative. We also need to update the value of x. We will take x, we will take negative of x if it is negative. Otherwise, we will keep the number positive. Now we will iterate for as long as x is greater than 0. So we will keep on taking out last digits. We will say that the new result, so let us say r new, is equal to, okay, this is Python. In Python, the overflow 32 bit will never happen. So we can directly compute the result. We can directly say that the result is equal to 10 times r plus x mod 10. X mod 10 will give me the last digit of any number x. So I'm just taking the last digit by doing modulus operator 10. And after performing this operation, I will reduce x. So let's say that my x, the value of x was 123. The last digit will be 3. I will reduce x by saying x is now divided by 10. So dash dash equal to is floor division in Python, which says that divide by 10 and then take the floor. So 123 divided by 10 is 12.3. Floor of 12.3 is 12. So I've sort of removed 3 from the number. It's now 12. In the next iteration, I will take 2 and remove 2. The number will become 1. In the next iteration, I will take 1 and the number will become 0. And then the loop will stop iterating. The loop will stop here. Okay, and then we can simply say we have to return this result. If it was negative, we have to return minus r. Otherwise, you have to return the result directly. And before returning, we can further check if this result lies in this range. So if this result actually lies in 2 to the power negative 2 to the power 31 and 2 to the power 31 minus 1. So if it lies in this range, that means it lies in this valid integer range, 32-bit signed range. Then in that case, if this does not lie, let us say that if this number does not lie in a valid 32-bit range, then we have to return a 0. If this condition is not true, that means it actually does lie in a 32-bit signed integer range, then we have to use this logic. If the number was initially negative, then we need to negate it once again. If the number was initially not negative, the result is the result. The end. Okay, me saying is not proof enough. Let us actually test this out. So I'm going to run my code and test it against the sample cases. Let us check. Okay, accepted. Let me use the sample test cases. Running this code, testing. Okay, it passes. Let us submit and see whether it passes all test cases or not. Fingers crossed. Success. All right, now it says that it is 44.74% faster. So like maybe half the solutions are faster than this. Don't fret about that. All we need to focus on is that all test cases should pass and that time complexity and space complexity is fine. Thank you very much for having me, guys. I'll solve more problems on LeetCode. See you in the next one. Ciao.